Swayam Prabha. Digital India. Educated India.
Welcome to Module 1, Lecture 4 of Concrete Technology. We shall be discussing today cement properties and tests. But before that, we shall be actually starting from where we have finished in the last class. So, we will talk of porosity of paste. Then we will look into properties and test on cement, setting, fineness, soundness, strength, and lastly we will look into types of cement. I will just start this types of cement. So, let us start from where we have stopped in the last class. We are trying to estimate the porosity in of cement paste. In our earlier lecture, we recognized two types of inherent pores in the cement paste. One, we called it as gel pores, which is a part of the structure of the product of hydration, and second one is the capillary pores. And also we stated, since the reaction takes relatively long time and is not instantaneous, but the structure, solid structure forms quickly. Therefore, as the hydration progresses, hydration product occupies the space that was originally filled by water, and that is how capillary porosity reduces, because capillary porosity are those pores which are left blank, which were actually originally water filled space and are left blank because hydration product could not fill those originally water filled pores. So, let us see, let us start from this figure, porosity of cement. If you recall, the last class we said, let us say C gram of cement, we add W gram of water to it, and with time hydration progresses. Let us say our degree of hydration is H, then unhydrated cement will be C into 1 minus H, because H is the fraction of cement hydrated. The fraction remain unhydrated will be C into 1 minus H by mass, and corresponding volume is given by this one, specific gravity of cement being known, it is 0.32 C, we can say 0.32217 C into 1 minus H. This is the unhydrated cement. CH is a mass of the cement that has reacted, because H is the degree of hydration, means fraction of cement that is reacted, and the volume of hydration product we know it is CH grams, 4.49 CH cc, 0.499 CH cc. So, volume of product hydration product CH gram is 0.49 CH cc, and then corresponding gel pores is 0.19 CH cc. So, we have derived all this in the last class. This is the space remain unoccupied and will be capillary will remain as capillary water, and this portion is empty capillaries, and we have also calculated this as 0.06 CHCC. Now, total initial volume of cement plus water is 0.317 C plus WCC or 0.32 C. Approximately this can be written as 0.32 C plus WCC. So, this is the total volume, and this volume is conserved because this will, as it hydrates, this will solidify quickly, and the skeleton structure will comprise of this total volume. So, hydration product must occupy this volume including the void spaces. Complete hydration product including void spaces must occupy this volume. So, these two volumes are conserved, and on this basis you shall be able to calculate out the volume of capillaries. So, volume of capillaries we calculate out as, because the total volume is conserved, the volume of capillary water is calculated as total initial volume minus volume of unhydrated cement, solid product of hydration minus gel pores and empty capillaries. So, what we are doing? We are actually subtracting from this total volume, we are subtracting this and this. So, we will get this volume. So, from this total volume we are doing this, and that is how we can get the volume of empty capillary or capillary water. Volume of capillary water, we can find out total initial volume minus volume of unhydrated cement, minus solid product of hydration minus volume of gel pores and empty capillaries. So, if we do that, this was known to us was a total initial volume was 0.32 C plus W. Volume of unhydrated cement is 0.32 C into 1 minus H from the previous diagram. Then volume of, this is the volume of hydration product 0.49 CH, solid product of hydration. Gel pore is 0.19 CH, and this is empty capillaries. And in this one you can see that 0.32 C and 0.32 C into 1, this will cancel out because there is a minus sign. So, you will be left with the rest of the things. So, this W will come here, right, 0.32 C H plus, this will be there because there is a minus sign here, there is a minus sign here. So, this is remaining here as 0.32, rounded off to 0.32, and 0.49 and 0.19 sum up gives us 0.74 CH, right, 68 CH plus 0.06 CH, all this sums up as 0.74 CH, because 0.49 plus 0.19 plus 0.06 will give me 0.74. So, this is 0.74 CH, and 74 minus 0.32, 74 minus 0.32 is simply 2042. So, I get volume of empty capillaries as W minus 0.42 CH, because this will cancel out together with this. So, left is W, and minus this minus and this minus makes it this, and rest of the term if I sum up I get 0.74. So, total I will get something like W minus 0.42 CH. Thus, the volume of empty capillaries, total volume of capillaries will be volume of empty capillaries plus volume of capillary water, and this if I sum up W minus 0.42 CH plus 0.06 CH, I get W minus 0.36 CH. So, total volume of capillaries in the system will be W minus 0.36 CH. Thus, I can get an expression for capillary porosity. I can get an expression for capillary porosity. All right. Capillary porosity will be volume of capillary pores divided by total volume. Now, what is the total volume? It is the sum of originally added cement volume plus water. Let us see. So, porosity is volume of pores divided by total volume, volume of pores divided by total volume. Capillary porosity is the volume of capillary pores divided by total volume, and the final volume is same as the total initial volume. Therefore, this is nothing but 0.32 C plus W. That is what we have seen, and therefore, capillary porosity will be W minus 0.36 CH divided by W plus 0.32 C, and if I divide both side by C, so this will cancel out, I will have W by C 0.32. So, you can see that capillary porosity is given by this formula, capillary porosity is given by this formula. All right. Similarly, I can find out the gel porosity. Similarly, I can find out the gel porosity, right. So, gel porosity will be what? Gel porosity will be volume of gel pores divided by total volume, volume of gel pores divided by total volume, and recall volume of gel pores were 0.19 H into C, and this was W plus this C. So, C, if I divide both side by C, I get 0.19 H, 0.19 H divided by 0.317 or 0.32 plus W by C. So, this is the gel porosity. So, if I sum this up total now, I will get the total porosity. So, total porosity is volume of gel pores, total porosity volume of gel pores plus capillary pores. Gel pores, volume of pores, total porosity I divide as volume of pores divided by total volume of pores divided by total volume, and this is nothing but sum of gel porosity plus capillary porosity, sum of gel porosity plus capillary porosity, and which will be if I sum it up. So, what do I get? Just let me do the summing. Point W by C plus okay, let me just do it like this. Let me do it here. W by C minus 0.36 H plus 0.19 H is equals to W by C minus 0.36 divided by 0.19 is 0.17. So, if I sum up volume of capillary pores plus volume of gel pores divided by C, of course, then just let me do it again. See, the capillary volume of capillary pores porosity was W minus 0.36 H divided by W by C plus 0.32 C plus 0.19 H divided by W by C plus 0.32 C. 3.317 is approximately equals to 0.32. That is what I am using. So, if you sum this up, you will get W minus 0.17 H divided by W by C plus 0.32. So, this is what you will get, because minus 0.36 plus 0.19 is equals to plus minus 0.17. So, this follows therefore, summing up these two will give me total porosity as W by C minus 0.17 H divided by this. So, this is how I can determine the total porosity of cement paste. Right. Now, you see, the total porosity of cement paste is important, but one interesting thing is that for complete hydration, the water cement ratio, minimum water cement ratio required for complete hydration, I can derive from these concepts. Now, if I have less water, then the originally water filled space will be small, and if it is small, the hydration product won't be able to occupy this space, because the space is not available. Because if the original water filled space is small, or proportion of water or water cement ratio is small, volume occupied by water would be small, and thus hydration product will not have sufficient space to fill in, sufficient space for itself to occupy. Now, it does not have very it does not the product, this product do not create any pressure, although cement with water after reaction expands, but it does not create pressure of this volume expansion due to hydration is not so high as to either disrupt the solid structure of the cement paste or create new space. So, hydration, maximum degree of hydration is limited by the originally quantity of originally added water, or in other words by water cement ratio. Let us see this. So, with progress of hydration, capillary porosity reduces and maximum degree of hydration will become 0 if I do not have sufficient space. So, therefore, you can see that capillary porosity is this, and for this to be 0, maximum degree of hydration is W by C by 0.36. In other words, if I have a water cement ratio less than 0.36, I will never have complete hydration. In other words, if I have water cement ratio less than 0.36, this term will be negative. You can't have negative capillary porosity. That means, you need more space than that is available. Therefore, water cement ratio less than 0.36, complete hydration is not possible due to lack of available space to be filled by product of hydration. This is because hydration is not instantaneous reaction. This reaction takes some time. Solid skeleton is formed within a short period of time. The solid skeleton will have capillary space within it, occupied by capillary water. As the hydration progresses, which progresses over a very long period of time compared to the initial setting time, let us say, or solidification time, this product of hydration would occupy the originally water filled space. Now, if you have less water in the beginning, you will have less space. So, product of hydration, where will it go? It does not have space. So, simply it will not be produced. That is how maximum hydration possible is limited for low water cement ratio, cement paste or concrete for that matter. So, if the water cement ratio is less than 0.36, complete hydration is not possible, right. At 0.36 degree of hydration, maximum possible degree of hydration is 1. But more than that, there are some other factors which we have seen in the last class, that water cement ratio, even with water cement degree of hydration is also a function of water cement ratio, and therefore, degree of hydration is a function of water cement ratio, and therefore, question of 100% hydration with age is just it is not there. It's simply it won't be there, because the degree of hydration is asymptotic to some value of function of water cement ratio. So, in any case below 0.36 it can never fully hydrate. Right. Now, we can look into consistency of paste. So far we looked into the porosity, which we actually continued from the previous class. Now, we can look into the consistency of paste, some properties. So, it is one important property is consistency of paste related to amount of water that is required to be added to make it uniform paste, because when you add water, when water is added, water makes the cement paste plastic. You add a little bit of water, it makes it plastic, and by progressive addition of water, air filled voids are occupied by water. So, in the original system, cement particles will have air filled space in between them. It is particulate system, they will have a given kind of packing, but within the grains or within the particles of cement, the void space will be filled by air. As I add water, this water filled space will be filled by air filled space will be occupied by water. Now, basic water content is achieved. So, you go on adding the water, a water content we call it basic water content, it is achieved when all open air voids are isolated by water to air bubbles. So, what happens? We will just see by a diagram that as you go on adding water, air paths were all interconnected. The interstitial space between the particles were all connected by air. Now, you add water, this space will be filled in by water. Now, when as then a situation will arise at certain point of time, as you go on adding water, a situation will arise at certain point of time when air filled spaces will become disconnected. Earlier they were all connected, but they will become isolated. That condition, the amount of water that is required to arrive at that condition, we call it as basic water content. We call it as basic water content, and it is achieved when all open air voids are isolated by water to air bubbles, and the corresponding consistency actually is normal consistency. So, corresponding consistency is normal consistency. If you add more water, it makes the paste softer and greater dispersion of cement particle may occur. So, cement particle can also get separated if you of course use a dispersing agent, otherwise the possibility of getting separated exists. They might be clogged, but each clogged system will be separated out by water. So, if you add more water, paste and mix it properly, the cement particles may be separated by water from each other. Let us see diagrammatically what it is, right. So, setting of course, important issue is setting test of cement is done at constant consistency. So, this is important, and initial water is non lubricating. At basic consistency, air bubbles are isolated. This is what we will look at. So, that is what we are saying. Consistency is important. Consistency per se may not be as important, but then we do setting test at a constant consistency. Now, how can you define a constant consistency? Of course, it was done initially empirically through a particular test, which we will talk about, but then this this water content corresponding to the standard consistency will not we can be defined really, and therefore, that is at that consistency we do the test. Now, that consistency correspond to basic water content as I mentioned, and consider this is a cement particle, another cement particle and another one and another one. They have a simple cubic packing. I am just for simplicity, I am assuming they have simple cubic packing. This has got simple cubic packing, right. For simplicity, we assume that this has got simple cubic packing, and the space here is air void. Space here is air void. So, as I add water, some of this void space are filled by water, a pendular state, nearly pendular state, not really pendular state. So, you have water filled here and air void inside, right, and air is still touching to the cement system, air is still touching to the cement system, and air voids may still remain interconnected. But if you add more water, let us say you add more water, a time will come when the air bubble will get isolated. So, this is my air bubble, this is the air bubble, and as it get isolated, this corresponds to basic consistency. So, when just they are isolated, that means just when the pendular state it is reached, that is what corresponds to basic consistency. And if you add more water, rapidly it will become the paste will become more plastic. Now, this standard consistency is this corresponds to about 26 to 33% by mass of dry cement. this corresponds to about 26 to 33% by mass of dry cement. How do we measure this? We measure this by an apparatus called Vickers apparatus. In fact, this instrument came first. The concepts of the basic consistency came much later. That was given by Power, in fact, in 1950s. This was in 19th century. So, this test, this is an empirical test, an empirical device developed in order to arrive at setting time, consistency, etc. of cement. Now, this apparatus has got, this is your cement in a mold, paste in a mold. The mold dimensions are given, not very important for our class to look into the dimensions. So, dimensions are given, and you have got a needle which are called Vickers needle. I mean more than one needle. You have, in fact, you have got first 1 millimeter square needle, and then this is a needle plus a small plunger. The small needle 1 millimeter square, then a plunger which larger diameter, and with a small gap between the tip of the needle and the plunger bottom, right. The dimensions are given. So, it can make an impression onto the paste like this. The center point, the needle will make an impression like this, and outside the plunger boundary will make an impression like this, and this is 1 meter square needle. This is a needle 10 mm square. So, these 3 needles are used to determine standard consistency, initial setting time, and final setting time. So, let us see what how standard consistency is determined. This needle one can lift it up and place it just on top of the cement here, cement paste here, and allow it to drop on its own. So, standard consistency is determined by this plunger, 10 mm plunger, that is this one, and its penetration should be, when the penetration reaches 5 to 7 millimeter from bottom. So, find out the time at which penetration. So, consistency, the time at which 5 to 7 millimeter from the bottom is reached. Now, that time, first you go on adding water. So, increase the water, start with the water maybe 25%, go on increasing 26%, 27%, etc., and find out the penetration. When the penetration can be, let us say total penetration can be 40 millimeter. Now, you measure the penetration from the top, because there is a needle has got a, you can measure the needle, there will be graduation, and if you measure from the needle how much it has penetrated. So, how much it is from the bottom, that you can find out. The water content or moisture, W by C expressed as percentage, when at which the needle penetration becomes between 5 to 7, that corresponds to standard consistency. So, this is, you can see that this is an empirical test, purely an empirical test devised by Vickers in order to come to that standard consistency. In fact, the basic water content which I talked about, this was postulated by T.C. Power and their team in 1950s, and first they looked into this basic water content, at which actually it becomes uniform, consistent, and after that rapidly it becomes plastic if you add any additional water. Now, they found that the basic water content, they actually, the term, the designated the water content which they designated as basic water content corresponding to basic consistency, that is same as the standard consistency, that you roughly same as the standard consistency that you obtain from Vickers test, right. So, standard consistency is this. Now, this test is of course important from the point of view that we test setting time at this water content, right, because you have to keep certain things constant. You want to find out setting time. So, consistency we keep constant, because fineness, the setting time may be dependent on fineness of the cement, but at the same time the fineness will also govern the consistency. So, a paste, how much water you should be added. We do not keep the amount of water constant, rather we keep the consistency constant and the water required to attain standard consistency, because some cases it may be very dry. Supposing the cement has got a very high standard consistency, requires a lot of water in order to arrive at that basic water content. In that case, if you would have kept the water content same, at a low water content, it would have been very dry. So, the penetration of the needle would not have been possible, right, not because of the cement characteristics, but because of the consistency or plasticity of the paste itself. So, plasticity is maintained constant and then setting time is measured, right, and this plasticity is related to the standard consistency, and that is why we got to get standard consistency. Let us see what we understand by setting again. We have discussed this a little bit earlier or few classes earlier, that it is actually cement becomes solid with time as the hydration as the reaction progresses. As the reaction progresses, it becomes solid with time, right. So, this solidification in a way is actually related to setting, and hardening is gain of strength. But strength gain do takes place during solidification also, because liquid, if you apply force, it simply deforms. So, it is in plastic state. I mean, liquid of course is deforms just on its own without any load. A plastic material is one where you put a constant load, it will go on continuously deforming, right. Liquid does not have a definite shape. So, it just deforms on its own weight, or just deforms straight away. You put it in any pot, it will take shape of that pot, a vessel, shape of the vessel. But a plastic material, you put any load, it will simply deform, all right. So, solid is one which has got a definite shape. If you want to cause its deformation, you have to apply load, and that is its deformation is governed by Hooke's law. So, stress strain relationship as we understand. So, therefore, during solidification some strength gain do take place, because after all from plastic to it is going to a solid state. So, let us see schematically we can represent. Initially it will be dormant period where there is no strength gain, y axis is strength, x axis is curing time, let us say. So, no strength gain. Then there will be rapid strength gain, right, and this process is setting. So, it will solidify, it has solidified actually, quick strength gain has occurred, but during the hardening process, this is the process of hardening, the strength gain will follow in this manner. So, this is what we understand. Hardening essentially is related to strength gain, setting is related to solidification, but do strength gain do occur during that period as well. Setting is measured again by this Vickers apparatus, but now you have a different needle. You use this needle. Initial setting time is for with 1 millimeter square needle, and penetration up to 5 millimeter from bottom signifies initial setting time. So, the needle has changed. Standard consistency is this needle, initial setting time this needle, and final setting time we use this, where this needle 1 millimeter square needle, this 1 millimeter square needle, which its projection is used such that when only this needle makes, this is projection, there is a small 0.3 millimeter projection. So, when this projection makes a mark onto the cement paste top, but this mark, the outer peripheral mark is not there, only the needle makes an impression, the other one does not make any impression. That means its penetration is very small, it is less than equals to 0.3 millimeter. The other one is not penetrating, this one is not penetrating, this end is not penetrating, this end is not penetrating, right, this end is not penetrating. That is called final setting time. So, when this is penetrating, this tip is penetrating, this end does not leave any mark, that we call as final setting time, So, this is how we measure the setting time, and this is the concept of setting time of cement, Particle size distribution of cement is important. In other words, fineness of the cement is important. Finer the cement, it will react fast, but at the same time it will require more water for wetting or standard consistency. So, fineness is particle size distribution of cement is very important. Finer cement can gain strength early, right. Now, how do you measure particle size distribution of or sizes particle size and its distribution of cement? Well, there can be several techniques. Highly instrumental technique like this is time of transition method, as it is called. This is called time of transition method. That gives us particle size. This is for, let us say, cement. So, varying from 1 micron to somewhere around 100 microns. This is for some cement, ordinary Portland cement, and another material, silica fume, which we will discuss later, shows particle size much smaller. Maximum is somewhere there, peak would be somewhere there. It is one particular silica fume, better one may have all particles somewhere there. So, you can see the cement particle size, but it is depend, this particle size and its distribution, that is what is the range of particle sizes. Mostly it is from about, this should be about 5 micron. So, 5 micron to less than 100 micron is the size of this particular cement by this method. But supposing you use another method called laser diffraction, you might get somewhat different. This is time of transition is also a laser based method. There are several advanced methods through which you can determine the particle size distribution of cement, but there are simpler methods which are also used. For example, we use specific surface, concept of specific surface. Now, specific surface is defined as the surface area per unit mass or maybe volume, which we will look later on. So, specific surface per unit mass or volume. Now, in case of cement, of course, you use surface area per unit mass. Now, you can see this. Supposing I have got spherical particle, for spherical particle surface area for a single particle is 4 pi r square, 4 pi r square, volume is pi r cube 4 by 3 pi r cube into rho, the density. So, specific surface will be equals to 4 pi r square divided by 4 by 3 pi r cube into rho will be equals to 3 by rho r. So, finer the particle, more will be the specific surface. Finer the particle. So, let me just write this again simply. Specific surface is 3 by r rho. Finer the particles, higher is specific surface. Therefore, specific surface, higher specific surface means finer particle, higher specific surface means specific particle. So, we determine in case of cement, surface area, specific surface, you see the cumulative percentage passing fraction, this is a sieve size maybe in microns, this could be in microns, and this is specific surface by a particular method is called Wagner methods. So, if you look at the size distribution, surface area has got a relationship with size distribution. If I can find out by particle size distribution specific surface or surface area, I can find out correspondingly. So, higher the surface size distribution, specific surface is in this manner. So, it is related. This Wagner method is based on Stokes law. What is Stokes law? I will not go into the equation, but supposing I have got a turbid mixture, right, particles are there in this one, finer particle, larger particle comes here below, larger ones, first large particle, larger, then finer particle. So, you might have done in soil hydrometer analysis. Wagner method is based on similar principle, but you can view this through optical method, number of particles at this depth, number of particles at this depth and other depths, etc., and you can get the specific surface. You can also determine the size distribution, and if you determine the size distribution, that is how the relationship is. Right. Now, most popular of course is Blaine's surface area measurement. You see, there are other measurement called Blaine's surface area measurement, and most popular is Blaine's method for measurement of surface area. So, let us see what does this gives, but before that it is important to mention that no two methods provide same result, and analysis is method dependent. Like time of transition, as I said, whatever particle size distribution it gives, laser diffraction do not give the same thing. Neither the hydrometer analysis will give you the same thing. If you do it through microscopy, won't give the same thing. So, there are problems, every method has got the problem, but they can be used for relative comparison. If you use same method, two cements can be compared, and which cement is finer than the other cement, that you can say. So, Blaine's method therefore is most commonly used, because it is a very simple method and test can be done in any laboratory without much difficulty. So, let us see Blaine's method. In Blaine's method, what you do is, you have actually a perforated brass disc here, a filter paper, and here this bed of cement. So, this one looks like this. This bed of cement, it's packed in a given manner with a plunger. This in this one we put a plunger, put fixed quantity of cement, put a plunger, and this volume is fixed. So, it is approximately assumed that it will have 50% porosity. So, cement particles are packed in a standard manner to have a particular amount of voids in them, right, porosity, and then this is placed here. This placed here. It has got a perforated brass disc. It is placed here. There is a filter paper here. So, nothing will go out, and they put the plunger from top. Nothing will come out of the filter. So, put the plunger on top and fix this dimension 1.5, etc., and then put it here. It is fixed here. Now, you have got a manometer. This is 1.5 centimeter thick bed with 0.5 porosity is prepared and fixed on top of a manometer with non-hygroscopic liquid to level 4, to this level, at this level, at the non-hygroscopic liquid is filled. Now, usually it is kerosene. So, you fix it up at this level, this is filled up to, initially it is filled up there. This distance is, marks are there 3, 2, 1, etc. Let us see. So, what we do is, we can, the distances are also available, we know how much is the head would be. So, what we do is, after we place it here, simple by simple suction, by simple hand manual suction, right. So, you can suck this air out of it, such that this liquid moves up to 1, this liquid moves up to 1. Air is evacuated up to liquid reaching 1. This is simply done manually by using a small small pump, you can say, is like the horn of a cycle rickshaw or something like that. You just or maybe suck it by mouth or something of that kind. So, simply this is evacuated so that this manometric liquid reaches 0.1. Usually it is kerosene or something of that kind, right. I mean non-hygroscopic liquid which will not absorb water, not kerosene, sorry, fixed, not kerosene, but some liquid which is non-hygroscopic, and then it is put to 1, just suck up to 1. So, vacuum is created, then close this valve, right, and note the time of fall of this liquid from, note the time of fall of the liquid from 2 to load the time of fall of the liquid from 2 to 3. So, from here to here 2 to 3. So, note the time required. So, what you do, you suck it up to this or evacuate it such that this liquid reaches here. then it will start falling. The moment it reaches here, you put on your stopwatch and stop the stopwatch at this point. The time is noted. This time, root over of this time is proportional to specific surface. There are some formula, empirical formula long, it need, we need not look into that, but this is proportional to k under root t. You can understand physically, if you have larger surface area. So, while if it is larger surface area, then friction offered to the flow of air, because from here to here you have actually pumped the liquid up. Now, liquid will fall because air will enter from the top, air will enter from this, air will enter through this. Now, to enter through this, the entrance of air, the quantity of or time required for air to cause drop of this manometric liquid from 2 to 3, 0.2 to 3, or reduction of evacuation from 0.2 to 3 by 5.5 centimeter is actually this from 2 to 3 will depend upon permeability of the cement bed here, permeability of cement bed here. If it is more permeable, then if it is more permeable, it will depend upon the surface area. Larger the surface area, time required will be more. If it is more permeable, time required will be less. If it is less permeable, time required will be more. Now, when it will be less permeable? When surface area it encounters is large. When surface area it encounters is large. So, surface area is proportional to under root t, right. Larger the surface area of the cement here, the air has to encounter while moving through this, right, it will take longer time. So, surface area is proportional to under root t. So, this is how we find out Blaine surface. Minimum specified for ordinary Portland cement is 2250 centimeter square per gram, 22 centimeter square, 225 centimeter square per gram minimum, or 225 meter square per kg, right. Most of the cements will have something like close to 300 etc. meter square per kg. So, most of the cements will have these values. We will come to this sometime later on. Now, let us see how do we determine free lime in cement. Free lime causes expansion, and we have defined the lime saturation factor as ratio of actual lime content to maximum lime content that can be allowed without producing free lime, right. Remember that we discussed, and this lime saturation factor also, this equation we have discussed earlier in the context of cement production. So, free lime is an important issue, because more the free lime, I will have cement will have unsoundness. So, soundness of test of cement is related to free lime, soundness test of cement is related to free lime or free magnesia. This is tested using Lee-Chatelier's apparatus, which is nothing but a split cylinder, which is nothing but a split cylinder with 30 millimeter inner diameter and 30 millimeter height. So, inner diameter is 30 millimeter and height is 30 millimeter, and it is 165 long indicator. So, it has got two indicators. You see, it is a split cylinder and there is a split here and there are two indicators here. So, what you do? Paste of standard consistency you place is stored in this word, is stored in water after covering with glass plates, and distance between these indicators are measured. So, you make paste inside this mold, right, and cover with glass plate at 18 degree centigrade, 18.9, 1.1 degree centigrade, and after that you measure. So, allow the hydration to progress, measure the distance between this indicator. The distance is measured, right, is recorded, and then it is boiled for 1 hour at 100 degree centigrade, and this distance is again measured. If the difference is less than 10 millimeter, it is fine. If not, a second test after aeration of the cement is done, and then the difference should be less than 5 millimeter. Magnesium. So, this is how soundness is measured. So, lime, free lime available, it will cause expansion, because it will become slacked lime. and it will cause expansion. Soundness test, common soundness test is done by this. Magnesia, test for magnesia, free magnesia is done by autoclave test. So, you put it under pressure and high temperature, right, cure it at high temperature, and using that autoclave test you can determine magnesia. Not very common, but this test is relatively common. Strength test of cement is done, not directly, because cement is never used as neat cement, and again this test is a means for comparing two cements. It does not give us, you are trying to compare the strength potential of two cements, not really anything to do with the strength of cement or cement paste, hydrated cement paste, not really. We are interested in finding out the strength potential of cement as a material. Hydrated cement paste is strength, we are not trying to look into that microstructure, gel strength and things like that, nothing. This is a tool for comparing, or this is a test method for comparing two cements, their strength potential in concrete system, if we may say so. So, what we do? We test actually mortar cubes for compressive strength. So, we use test on mortar 1:3, 1 cement, 3 sand, and this sand is standardized. So, that standard, and the cube size is 7.07 centimeter square side length. In other words, 7.07, this will be 50 centimeter square. So, you test 50 centimeter square cube and cast them in standard manner. Mixing water is related to consistency by a formula, or 10% by mass of dry material, total dry material, close, cement and sand, 10% by mass of dry material, or in some course it is related to P, standard consistency, right. So, then this is cast, these cubes are cast, demolded after 24 hours and cured for 7 or 28 days. This casting is done in a standard manner, even compaction is done in a standard manner. The vibration has to be in a standard mold, standard vibrating machine, everything else is standardized. You use standard cement, standard sand, only cement is the variable. Quantity of water is fixed by the code related to consistency, or as I said, some cases 10% of the mass, 10% by mass of dry material, and then demolded after 24 hours and cured within at a fixed temperature, specified temperature for 7 days or 28 days, and then tested wet in a standard manner at 35 MPa rate of loading per minute. So, at a fixed rate of loading, because all this affects the strength of those cubes, the rate of loading, and the material itself will depend upon its hydration, etc., will depend upon curing condition. So, we fix the curing condition, temperature is fixed, temperature of curing is fixed, temperature of casting is fixed, casting is done in a standard manner, the only variable is cement. So, we can compare two cements, their strength potential in concrete by this test. Although, it is not necessary that you have a higher strength cement, you will get the proportional increase in strength of concrete, that is not necessary, but this can compare two cement, and you can have specifications of cement based on this test results. So, if you have higher strength, it will have higher potential of strength. Specific gravity is measured by Leach-Atelier's flask, which looks something like this, right, and we put first liquid, something like kerosene, which do not react with cement, and the increase in volume is what is observed. There are graduations here. So, you put the cement, first the liquid, fill it up, then put those solids, see how much is the increase in volume. This is weight, fixed mass. So, what you are doing, first is this Leach-Atelier's flask is filled with kerosene, then known mass of cement is added from measurement, and increase in volume is found out. So, from increase in volume of this cement is found out by driving air bubbles. So, you drive out all the air bubbles and find out how much, due to by putting these solids here in the flask, which was filled with liquid like kerosene before, how much is the increase in volume. So, this volume of these particles are measured, its mass is known, specific gravity can be found out. Typically, it is 3.15. Typically, it is 3.15. 3.15, the value is 3.15 or close to 3.15. Right. So, I think this is what largely we wanted to discuss today, but I will discuss types of cement in the next class, because what we know is the hydration process is a function of the compound composition. Depending upon type of compound, hydration will progress at a faster or amount of compound, which compound has got how much quantity, because we have seen C3S is responsible for high early strength. Similarly, C3A is responsible for high heat of hydration. So, if I manipulate the composition of the cement, properties can be altered. So, when we discuss type of cement, we will discuss this. So, we will discuss this from this slide onwards in the next class, that by modifying composition, and physical properties, because physical properties means fineness, for example. So, by modifying physical properties and composition of cement, their properties can be changed favorably to obtain various types of cements, and this is what we will discuss in the next class. For example, OPC is the first type of cement, RHPC is the second kind of cement, rapid hardening Portland cement, ordinary Portland cement, low heat Portland cement, sulphate resisting cement, blended cements of various kinds, and super sulphated cement. We will discuss all of them, white cement, so many other expansive cement which will expand, and various other kind of cement. So, I think with this, this would be the composition. I will look into this in the next class. So, with this we can summarize types of cement we will discuss in the next class. We have actually discussed to the porosity, which we could not do in the last class. So, we continued from there, discuss the various formulae, derived various formulae for porosity. Some numerical problems can be solved easily on those, right. I really did not solve a numerical problem, but simply you can find or estimate the porosity using those formulae. Then we also looked into some properties of the cement and corresponding tests, and we introduced you types of cement. Next class we will look into the types of cement in detail. So, thank you very much.